Project 2.4.3, ISP Medium, the transistor-based binary coded decimal decoder. The goal of this project was to build the 4511 BCD decoder chip out of transistors to combine with Liam Northup's binary counter to make a complete counting circuit out of transistors. My device functions both independently with an Atmega 328P generating BCD signals, as well as in cooperation with Liam's device or any external binary counter. Here's how it works. I've unscrewed it to show you the inside. There's an internal battery, so I can turn the device on with this switch. The Atmega 328P generates BCD signals in succession form from 0 to 9 so that the transistors decode and output it onto the 7-segment display. It includes the blank input and lamp test features of the IC, but not the store feature, which were also made with transistors. I can turn the counting circuit into manual mode. Here's some numbers: 8, 9, 1, 3, 7, etc. So in manual mode, I can choose which values to display with the dip rocker bank. Also, I can reset the count and switch it to counting down. If I flip this switch, the device goes into external mode and shuts the Atmega off and takes input from any external binary counter. Here it is with Liam's device. I've taken the Atmega out so you can see that it is actually taking signals from his device and not the Atmega. Notice that the numbers 4 and 6 aren't displaying correctly. Both of our devices work individually, so we're guessing this happens because I have a 9-volt battery powering nearly 300 transistors if you include Liam's, so there isn't enough current for all transistors to function properly. That was the blank input, and this is the display test. Before building with transistors, I built a prototype of logic gates to confirm it would work. Here's that circuit in action. I then built one segment out of transistors to confirm that the transistor would work. Here's segment B, and notice that it's only off for 5 and 6. It also works with the blank input and display test features. So here for 5 and 6 it's off, but the display test keeps it on. Here are 4 logic gates made out of transistors. Note that each base has its own resistor, and that is to avoid current hogging, which would make the gates not function correctly. This is a dual input AND gate. The output is only on when both inputs are on. In the AND gate, at rest, current flows through this transistor, turning it on. And that means current flows through here, straight to ground, and not through this LED, so the LED is off. However, when both of these transistors are turned on, then current can flow through here to ground, and it doesn't turn this transistor on. So when this transistor is off, then current can go straight through the LED, turning the output high. An AND gate built like this would function in theory. However, BJT transistors leak a small amount of current from the base to the emitter, so turning on the second input activates the second transistor, causing the output to turn on and breaking the AND gate logic. This is a triple input OR gate. The output is on when any one of the 3 inputs is on. In the OR gate, current goes through this transistor, turning it on, so that means all the current goes through this transistor to ground and the LED is off. However, if A is on, then the current will go through to ground, so this transistor goes off, so then the LED can go on. Or if B goes on, then this transistor is on, so once again the current can go to ground here, it doesn't go through this transistor, and it turns the output on. An OR gate built like this functions in theory and practice, but does not work well in larger circuits because it is not in a proper pull-up configuration. There's a voltage drop of about 0.7 volts across the base emitter junction, so with multiple OR gates in series, the output voltage drops several times, and it isn't high enough to power a 7-segment display. This is an XNOR gate where the output is on only when the inputs are the same. In the XNOR gate, if A and B are on, then the current goes through ground through here, and if this current goes through ground, this transistor is off, so that means the current can go straight through this LED, turning it on, because it can't go through one of these transistors to ground. However, if A or B is on, but not both of them, then one of these transistors will turn on, so then the current can go through one of these transistors to ground, because this transistor will be on, because not A and B are on. And this is a NOT gate, which inverts the input. In the NOT gate, current goes through the LED, turning it on. However, if the switch goes on, then current goes through this transistor, turning it on, so that causes current to go through the transistor to ground and then not through the LED, turning it off. Now, how do the binary inputs actually get decoded? Well, here's an example. The segment A is on for every number except for 1 and 4. So we need to make a Boolean algebra equation that takes signals and produces a high only for 0, 2, 3, 5, 6, 7, 8, and 9, but not 1 and 4. Well, by adding A or C to the equation, we cover 2, 3, 6, and 7 just from the C, and we cover 8 and 9 just from the A. Notice that A or C aren't high in 1 and 4 because that would break the logic. This leaves us with 0 and 5. By XNORing B and D, where B and D being the same produces a high, we cover 0 and 5. And notice that B XNOR D in these equations produces a low. By repeating this process of figuring out an equation for all 7 segments, the equations for the BCD can be decoded. Here's a diagram showing when all 7 segments are high or low. Here are the 7 derived equations. Because they contain a lot of overlap in common logic equations, intermediate gates can be formed to simplify the equations tons. Finally, the display test and blank input. The display test is low during normal operation, but when switched to power, it turns all segments on. This is because the result of all 7 equations are ORed with the display test switch. So essentially, the segment is on if the equation tells it to be on, or if the display test is high. The blank input is high during normal operation, but when switched to ground, it turns all segments off. This is because the results of the 7 equations and display test are ANDed with the blank input. So when the blank input is low, the result of the AND gates are low, so all segments go off. Thank you for watching my project.